So this is exercise 1.2, R D Sharma. Okay. Question number 1, show that the relation are defined by are equal to a comma b such that a minus b is divisible by 3. A b belongs to z is an equivalence relation. CBSE 208. Okay. R such that r equal to a comma b, a minus b is divisible by 3. A b belongs to z. For reflexive, a minus a equal to 0 into 3. A minus a divisible by 3. That implies a comma a belongs to r for all a belongs to z. That implies r if r is reflexive. Symmetric, a minus b is divisible by 3. A minus b equal to 3p. P belongs to z. B minus a equal to 3 into minus p. Write it here. Minus p belongs to z as p belongs to z. B minus a is divisible by 3 and b comma a belongs to r. For all a comma b belongs to z, r is symmetric. Transitive. Let a comma b and b comma c belongs to r. A minus b and b minus c are divisible by 3. So a minus b equal to, that implies a minus b equal to 3p for p belongs to z and b minus c equal to 3 cube for q belongs to z. Add a minus c, a plus b, a minus b plus c, b minus c. So 3pu. Okay. So this should be written here. This is a continuation of the problem. Write it beside this. As p and q belongs to z, so p plus q belongs to z also. Okay, write this thing in the this right hand side. Okay,
Okay.
so r is transitive. R is transitive. So next you have to write that r is, therefore r is transitive. Okay, first write reflexive, symmetric, and transitive. Hence R is an equivalence relation. So just don't check that this R is reflexive, symmetric, and transitive. So at the end you have to write this also, that yes, R is reflexive, symmetric, and transitive. Hence R is equivalence relation. Question number 2. So that the relation R on Z of integers given by r equal to a comma b 2 divides a minus b is an equivalence relation. This is same same problem. You can ignore it. Question number 3. Prove that R is a relation defined on Z defined by a comma b belongs to R if and only if a minus b is divisible by 5. These all are same problem basically. Yes, these all are same problem, and in the at the end you have to write R is reflexive, symmetric, and transitive relation. Hence, R is an equivalence relation. Okay, you have to write at the end. So this is again question number 5. Let n be the fixed positive integer. That means n belongs to natural number, and a minus b is divisible by n. This is also same problem. Here, instead of 2, 3, or 5, it is given a general integer n. That is also belongs to natural number n. So 5, let be the set of integers. Show that the relation r equal to a comma b such that a b belongs to z and a plus b is an equivalence relation on z. So I will check this. Question number 5. R equal to AB such that AB belongs to Z and A plus B is even. Okay. So for all A belongs to R, again we have written A belongs to R. A belongs to the set of integers. A belongs to Z. A belongs to Z. A plus A equal to 2A, and you should write here which is an number. Even number that implies A comma A belongs to R and R is reflexive. A plus B is even, B plus A is also even. Now B comma A belongs to R is symmetric. So A plus B equal to 2Q and B plus A equal to also 2Q. Now A plus B and B plus C is even. Um, A plus B. So here it is A plus B equal to 2Q and B plus C equal to 2P. Let's suppose 2P. Now we have to show that A plus C is equal to also this some 2Q form. Now so here it is 2y, not only 2x and 2y. Where this xy came from? You have to write this fast. Like 2p or 2q, and then A plus C equal to 2p plus q minus 2b. Now you have to write p plus q minus b. Now as p, q and b all belongs to z, that means that implies p plus q minus b belongs to z. Okay, so A comma C belongs to R, and hence R is transitive. Now you have to write R is an equivalence relation. So before that, you have to write R is reflexive, symmetric, and transitive. Hence, R is an equivalence relation. Because you have to prove that R is an equivalence relation. They have asked to prove R is an equivalence relation. If you prove R is reflexive, symmetric, and transitive, then you have to write that because R is reflexive, symmetric, transitive, and hence it is equivalence relation. Question number 6. M is said to be related to n if m and n are integers and m minus n is divisible by 13. Does it define an equivalence relation? Divisible by 13, 0 into 13. Okay, write it here as p belongs to z minus p belongs to z implies n minus m is divisible by 13, n comma m belongs to r for all m n belongs to z. R is symmetric and okay, oh, again you have to write 7. Let R be a relation on the set of order pairs of non-zero integers defined by x, y, r, u, v if and only if x, v equal to y, u. Okay, so that R is an equivalence relation. Okay, so here it is a comma b belongs to a. Where is a? What is a? You are you have you are given a specified set, that is z plus, sorry, z star. Z star means non-zero integers. Z plus mean positive integers. I mean that is natural numbers. So why you have written a here? So this is a comma b and a comma b because for reflexivity both are same element. So first multiplied with fourth and second multiplied with third. So ab equal to ba for all z star. Are you following?
Yes.
So ab equal to ba, that means a comma b related to a comma b, hence reflexive. Now here, x comma y and u comma v belongs to not a, it is z star. So x v into equal to yu, this implies vx equal to uy and uy equal to vx. Okay, that implies. So you have to write it here that u y comma x related to v comma u, v comma u. Sorry, not this. This is not okay. So you don't need this one. You don't need that vx equal to uy. You need only this yu equal to xv, and okay. Next, uy equal to vx. So write this uv related to xy, and hence it is symmetric. R is symmetric. Next, there are three, I mean, elements that are x comma y, next p comma q, and this is actually u comma v. This okay. This should be, you should write this z cross z. Okay, z cross z star, because a belongs to z star and b belongs to also z star. So a comma b belongs to z star cross z star. Okay, so these three belongs to z star cross z star. Okay, so now x comma y related to p comma q, and u p comma q related to u comma v. Now is it told to prove it is a equivalence relation? So that R is an equivalence relation. Okay, it is an equivalence relation. So from this, it implies that xq equal to yp, and from here it implies that pv equal to qu. Okay, now we have to show that x v equal to yu. This we have to show. Okay, this implies that okay, x by y equal to p by q, and from here we get p by q. From here we can get p by q equal to u by v. So that implies x by y equal to u by v. This implies x b equal to u into y. Oh, that implies x comma y related to u comma v. So that implies x r is transitive relation. So R is transitive, reflexive, and symmetric. So hence R is equivalence relation. I hope next time you will write this thing at the end. Question number 8. Show that the relation R on the set x belongs to z such that x is greater than 0 and less than equal to 12 given by a comma b such that a equal to b is an equivalence relation. Find all the set of elements related to 1. Okay, x belongs to a, x is equal to b, a is equal to b square or b cube, what is written here? Okay, a is equal to b. Okay, okay. A comma a equal to b. Let a comma b belongs to r. A belongs to r. Again, you have written yesterday, the previous class, that a belongs to r. I have told you that a r is the relation, and you are taking that element from the set. So a belongs to z, and a is greater than 0 and less than 12. So basically, you don't have to write this thing. Just write the relation r. This is 0 comma 0, 1 comma 1, 2 comma 2, 3 comma 3, and so up to 12 comma 12. This is the relation, and this is the reflexive relation. And I have told that the reflexive relation is the smallest equivalence relation because it is reflexive, symmetric, and transitive, all of the three. And if this, so again in the last question, find the set of all elements related to 1. This, the elements which is related to 1 is only the 1. 1 is only related to 1. 1 related to 1. So the class of 1 is only the set 1. Here both, all the class from 0 to 12 contains only one element, the that element itself. Okay, so this is something to be noted. Now question number 9. Let L be the set of all lines xy plane. R be the relation defined as R equal to L1 comma L2. L1 is parallel to L2, so that R is an equivalence relation, and set, find the set of all lines related to the line y equal to 2x plus 4. Okay, this is something interesting, the last part. So L is parallel to itself, hence L comma L belongs to R, and L is coming from, you have to write script L. So L1 is parallel to L2. If L1 L2 belongs to R2, then R L2 L2 comma L1 belongs to R. So write L1 L2 belongs to script L, and L1 parallel to L2 implies L2 is parallel to L1. Okay, this is symmetric and this is transitive also. So the line L equal to the equivalence class of line L equal to L such that I would write L such that y equal to 2x plus 4. This class is L such that y equal to 2x plus c. This is the class. Okay, right. Next question number 10. So that the relation R defined on the set A of all polygons as P1, P2. P1, P2 have the same number of sides. This is also easy because if P1 and P2 has same side, then P2 and P1 has same side. That means P1, P2 belongs to R and P2, P1 belongs to R. So all are same. So, at the last, what is the set of all elements A related to the right angle triangle T with sides 3, 4, 5? Okay, this is something interesting. What is OP? P, P belongs to R. For all P belongs to A. Now, after 4 or 5 classes, if I correct you like this, then it is not desired. P belongs to A. For all P belongs to A. PQ, all I will not check this because this is a routine task. Now you did not solve this 3, 4, 5, 3, 4, 5. This type of triangle. So here the relation is saying that P1, P2 are related whenever they have same sides. So 3, 4, 5 is irrelevant because it is talking about triangles. It has 3 sides. Whatever be the sides, it has 3 sides. We have to focus on the number of sides. So all the triangles are related to 3, 4, 5 sided triangle because here 3, 4, 5, I mean this is a right angle triangle. Though this is a right angle triangle, because of the relation defined here, it is irrelevant of the sides. It is not I mean significant for us that it is a right angle triangle. Though as it is a triangle, all triangles are related to this triangle. Okay?
Okay.
Now 13. Okay, 11. Let 0 be the origin. We define a relation between 2 points P and Q in a plane if OP equal to OQ. Now, so that the relation so defined is an equivalence relation. So, okay, this is a good problem. Okay, so where is 11? Oh, this is 11. Where is 10?
At last.
So this is 11. Okay. OP equal to OP. So P comma P belongs to R. So where is P is coming from? P is coming from the set of, it was mentioned here. So P is coming from a plane. Okay. Is coming from a plane. P is coming from plane. Okay. Let's write it set of all points on a plane. So again we will name it as script P. Okay. So P is coming from script P. So this is symmetric and this is also transitive. Okay. I will remove this. Okay. So so that it is an equivalence relation. Okay, that's right. Let R be the relation defined on the set 1, 2, 3, 4, 5, 6, 7 by A comma B. Both A and B are either odd or even. So that R is an equivalence relation. Further, so that all the elements of the subset are related to each other and all the elements of the subset 2, 4, 6 are related to each other, but no element of the subset 1, 3, 5, 7 is related to any of the element of the subset 2, 4, 6. Okay, this is very good. So okay, this is not 12, this is 13. So again, once again you have to write here that R is an equivalence relation. Before that, R is a reflexive symmetric transitive relation. Okay, so question number 13. Let S be the relation on the set R of all real numbers defined by A comma B belongs to R cross R. Okay, A square plus B square equal to 1. Okay, this is proof that S is not equivalence relation on R. Okay, okay. So A belongs to R. A belongs to R. a square plus a square not equal to 1. Why a square plus y square is not equal to 1? You have to give some example. Because a square plus a square equal to 1, this implies that 2a square equal to 1 and a square equal to half. That means a equal to plus minus 1 by root 2. So not for all. So you can write this for only a equal to plus minus 1 by root 2. A comma a belongs to s. Okay. So so s is not reflexive relation. Next, it is symmetric because a square plus b square equal to 1. That means b square plus a square is equal to 1. And a square plus b square equal to 1. That means, and b square plus c square equal to 1. So, is not symmetric. A square plus c square. Okay, here you have to give an example. So, because 1 by, okay, let us take 1 by root 3 and root 2 by root 3. All are real numbers. They are irrational but real numbers. And take, okay, no. Sorry. Here is it is transitive because if a square, then what is b square? B square equal to 1 minus a square, and here also b square equal to 1 minus c square. So 1 minus a square equal to 1 minus c square. That implies a square equal to c square. That means a equal to plus minus c. Okay. So whenever a square and b square equal to 1 and b square plus c square equal to 1, that means a equal to plus minus c or c equal to plus minus a. So that means a square plus a square plus b square equal to 1. This is equal to b square plus c square. This implies a equal to plus minus c or c equal to plus minus a. That means a comma b belongs to s and b comma c belongs to s. This implies that a, I mean b, sorry, a equal to plus minus c. That means a comma b and b comma, so here we will write the reverse, c equal to plus minus a. Either it will be b comma a or it will be b comma minus a. Okay, so this is transitive. Okay, like this, suppose this is 1 comma 0 and 0 comma 1. Okay, okay. So here is an example. 1 comma 0 and 0 comma 1 belongs to both belongs to S, but 1 comma 1 does not belongs to S, because 1 square plus 1 square is equal to 2, right? So okay.
Yes.
Okay, so A square plus B square, it is not symmetric, it is transitive. A square plus B square equal to 1 and B square plus C square equal to 1. This is not correct. You have to give an example. This is an example. 1 comma 0 and 0 comma 1. These two belongs to S, because 1 square plus 0 square equal to 1 and 0 square plus 1 square is equal to 1. But 1 square plus 1 square, which is equal to 2, is not equal to 1. That means 1 comma 1 does not belongs to S. That implies S is not transitive. Okay, 14. Let Z be the set of all integers and Z0 be all set of integers, non-zero integers. Let a relation R on Z cross Z0, okay, be defined as follows: A comma B and C comma D related to each other if and only if AD equal to BC. AD, AB and CD belongs to Z cross Z0. Prove that R is an equivalence relation on Z cross Z0. So here it is same as this problem. And where was this problem? This xy in equal to yu. But here there was in this problem number 7, there was all both the set were non-zero integers, and here it is one is integers and one is non-zero integers. So AB belongs to Z cross non-zero, Z cross Z0. It is not correct. A belongs to Z, B belongs to Z0, and AB equal to BA. B not equal to 0. I mean, here B not equal to 0, because AB in the problem number 7 we wrote this AB equal to BA because both were non-zero, and here one is non-zero. I mean, B is non-zero. That is why we can write AB equal to BA. So you have to mention that here B is not equal to 0 because B belongs to Z0. Okay, so AB belongs to R, so it is a reflexive relation, and ABCD belongs to Z cross Z0. AD equal to BC. This implies CD equal to DA. CB equal to DA. So here B and D, here B and D not equal to 0. Okay, so AB, CD, A related to AB related to CD implies CD related to AB. R is symmetric. So here it is given that Z cross Z0. That is why you have to be careful about these things. Okay, next AB AD equal to BC, and here again for the transitiveness you will use AB C, D, and E, F. Then this B, D, and F, B, D, comma F belongs to Z0, and A, B, C, A, C, E belongs to Z. So when you are writing AD equal to BC and CF equal to DE, now when you applying the quotient, that is, we have to prove AF equal to B. So this is A by B equal to C by D. So here it is given that D not equal to 0. That is why you can write it. So C by D equal to E by F. D not equal to 0. Okay, 1 second. No, 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 no. D not equal to 0 and okay, B also not equal to 0. B, comma D, comma F all are not equal to 0. That is why we can take it in the denominator. B, D, and F not equal to all of these three not equal to 0. So that is why this quotient is valid. And hence we can write AB equal to EF. And here we can write AF equal to EB. And this implies AB related to EF and it is transitive. Okay. Question number 10. P1, P2 have same number of sides. P1 for all A. P. Okay. P has same number of sides as P. So P comma P belongs to, for all A, belongs to R. P comma P belongs to R for all P belongs to A. Okay. So this is okay. Equivalence relation. And okay. You have not right 3, 4, 5. This set is the all set of all set of all triangles. Okay. What was this? Okay. AB either even or odd. Both even or both odd. So this is an equivalence relation. Okay. But why 1, 3, 5, 7? These are set of all set of odd integers. Okay, which is less than equal to 7. And this is 2, 4, 6 set of even integers less than equal to 7. These two are different set, disjoint set, because if we take 1, 3, then both are odd. So 1 related to 3, 2 related to 4, because 2 and 4 both are even. But 1 is not related to 4 because 1 is odd and 4 is even. So this is why 1 does not related to R, 4. So in this set, everything is related to itself, related to each other in this set, related to each other with the relation by the relation R, and in this set everyone is related to each other by the relation R, but no element of this set is related to this no element of any of the element of this set by the relation R. Okay, hope you understood it. Okay, everything clear?
Okay. Yes.
Okay, once 16, 14, 15, 15. Have you solved 15? Question number 15.
Yes, I've solved.
If R and S are relations on the set A, then prove all the following. R and S are symmetric implies R intersection S and R union S is symmetric. R is reflexive and S is any relation implies R union S is reflexive. What is 15? Yes, this is proof for R intersection S. So R was uh, R and S relations on set A. Then prove the following. R and S are symmetric implies R intersection S and R union S is symmetric. Okay. So you have to write before that R and S are relations on A. Write those things so that the whoever is checking your answer can understand clearly. So R and S are relations on A and R for the first proof R and S are symmetric. So proof R AB belongs to R intersection S. That implies AB belongs to R and AB belongs to S. Okay. So you have to write this BA belongs to R and BA belongs to S because as R and S are both symmetric, that implies R intersection S is symmetric. R union S, proof for R union S. If A B comma B belongs to no this not this. Let A B belongs to R union S. That implies A comma B belongs to R or A comma B belongs to S. That implies B comma A belongs to R or B comma A belongs to S. Because in the right hand side you should write R comma S are symmetric relation. So that implies B comma A belongs to R union S. So that's complete. Okay, now um, What is this part? Okay. Now R was a reflexive relation and was a any relation on R A. So R is reflexive. Then one second. R was reflexive and S is any relation. That implies R union S is reflexive. This is also very easy. So A belongs to A comma A belongs to R for all A as R. Okay, you should write this at first as R is A. You should write first as R is a reflexive relation. Therefore, for all A belongs to A comma A belongs to R, and A comma A belongs to R union S for this, not this, any S, for any S belongs to, sorry, this is a relation on A, so that means this is a subset of A cross A. So that implies R union S is reflexive. Okay. Okay. So relation topic, the chapter relation is finished, right? Okay. So you have to do the exemplar problems. I have sent you the PDF of exemplar of relation function chapter. You have to do this. Okay.
Okay.